Hi, I'm Julian Togelius. So I'm an associate professor at New York University, where I direct the Game Innovation Lab, where we do research on AI for games and games for AI, which is closely related, but not quite the same. I'm also co-founder of Model.ai, where we do not exactly the same things, but related. We're trying to model human behavior and experience. That's a great question. I mean, the romantic in me wants to see it as this is the search for actual, true intelligence. So basically, when I got started, I did not want to work with any kind of computer science, engineering or so, because I didn't want to touch maths. I studied philosophy and psychology because I wanted to understand the mind. I wanted to understand how intelligence worked and what consciousness is and how it comes about. So I gradually segued into computer science because I figured out that there you could actually do stuff, and I needed to build a mind to understand it. So if you ask me on a romantic day, I'm trying to solve the quest for real intelligence, real general intelligence. If you ask me when I'm on a more pragmatic mood, I'm trying to come up with ways to make humans do a way to make computers do things which currently only humans can do. Yeah, so what guided my work on evolutionary algorithms is that I wanted ways to deal with these very badly formulated, badly constrained problems where you don't have very clear sort of error functions. So I started out wanting to learn very general sort of behavior that could solve agent that could solve many different tasks, and where the tasks were not necessarily very well defined, and it was really hard to find good error signals that you could use to train a network. So I sort of took to evolutionary computation, and nowadays I still do that, and also do a lot of work on evolutionary design, where by nature the error function or the objective function is very complex and hard to formulate. You might need humans to sort of implement it, so to say. But I mean, beyond that, I'm also very fascinated by evolution itself, as many of us are. So much of my work deals with learning to play games, and you may think that that's a very well-defined question, because what is it like to play a game well? Well, that's getting a high score, getting many points, for example, or surviving very long in a game. That's true, but in many cases, you, for example, want algorithms that play in many different ways, that have a range of interesting behavior, and suddenly you need diversity as well as quality in the solution you're finding. And that drove me towards evolutionary algorithms, because you have all these different ways to come up with diversity in your solutions. And this goes for design problems as well. So the reason I'm using evolutionary algorithms as one of my core sort of methods of implementing certain kinds of artificial intelligence is both the versatility they apply to so many different things, and their capacity for dealing with both quality and diversity at the same time. It can help AI become smarter, partly because when you look at artificial intelligence, it's really a lot of different ways of solving problems. And what you want to do is that you want to minimize the amount of work that goes into specifying the solution yourself, the amount of programming you have to do yourself. And artificial evolution is the most general way of searching the space of potential solutions so that you can find solutions automatically rather than having to create them on your own. Yeah, so I did a series of experiments where I was training neural networks to drive racing car in a simple racing game. So interesting enough, a very simple evolutionary approach worked pretty well when it came to evolving a neural network that would drive this racing car, and it pretty quickly learned superhuman performance. So it drove really, really well. And it drove better than me. We took it to a conference, asked lots of people to drive against it, and it drove better than them. But then we tried we're putting it on another track that was simply the same track but mirrored, so you have to take the turns in a different order. And it didn't do well at all. What it turns out that it had done was that overfitted to this particular track. So it had learned driving behavior that was only good in one particular situation. It's like you're learning to drive a car, but you only really learn to drive between your home and your work, and you can't deal with if someone tells you to go drive to the grocery store instead. So what we did was that we came up with a scenario where every time it learned to drive a track, we added another track to the fitness function. So eventually it was training every time it was a new network was trained on 8 different tracks. And this is called incremental evolution. And we got really, really good performance with this. So by training on simple tracks and eventually and gradually introducing more and more complex tracks with more and more different challenges, we eventually learned to drive on really complex tracks which we could not learn to drive at in the first place. So this was really nice. We can then specialize these neural networks to drive on very particular tracks again and get really, really high performance. Now, then there was another problem. Through all this time, we had the car driving on its own with no other cars present. So we tried putting other cars in there, and it was a disaster, and it just crashed. So we then start to use something called competitive coevolution, where we train one population of neural networks to drive as well as possible, and another population of neural networks to drive as well as possible as well. But they were tested with each other, so they were both on the track at the same time. And this means that your performance is affected not only by how well you drive, but also how well your competitor drives. And by varying the fitness functions here, so whether the fitness is to drive as far as possible within a given time, or whether the fitness is simply to drive faster than the other car, you get very, very different behaviors. Needless to say, basically, if you just tell them to drive as far as possible on their own, they will mostly avoid the other car and basically drive nicely. Now, if you tell them that what matters is to drive faster than the other car, well, you get this situation, if you're running from a lion, you don't have to run faster than the lion, you have to run faster than the other guy. So that's what happened. We saw complete mayhem, which sometimes may be desirable if you're creating a video game agent, for example. And by basically changing these parameters of the fitness function, you can get really good and interesting behavior emerging here from the evolutionary process. You get very similar phenomena in first-person shooters. So we created we did an experiment where we evolved neural networks to play first-person shooter games. So first-person shooter games are complex tasks that require you to perform sort of fine-level motor movement. You need to aim well, and you need to run around and sort of avoid bullets. But then you also need to do actions that play out of a slightly longer time scales. You need to explore the area you're in, and you need to find health packs when your health is low. You need to find other weapons. Maybe you learn to ambush other players, and so on. So what we did was that we created a layered controller. So we had we first trained a neural network to play a particular, to sort of do the low-level stuff, to run and gun essentially. And then we had another layer that dealt with exploration, and another layer that dealt with like finding health packs when you need it, etc. And you can sort of basically build up layers of a controller, like layers of a human brain. Like, I mean, in real evolution, our brain, we talk about the reptile brain and the mammalian brain and the human brain being on top of each other, which is not just a figure of speech. Our biology basically looks a bit like that. So we replicated that within an evolutionary setting where we evolved increasingly complex general behavior by incrementally adding fitness functions and new networks on top of the previous networks. Games are fantastic because, why do you think games are fun? I mean, you think games are fun, right? We all think games are fun. And they're fun partly because they teach us. They teach us how to play them. A good game is a good learning experience. And they have this smooth difficulty curve where you start and you don't know anything about the game, and then you sort of you learn how to do the basic stuff, and it gives you more challenges, and then you sort of, when you master them, it gives you even more challenges. So they are like very good pedagogical tools. At the same time, they're also fun because they are engaging our minds. You think you're relaxing when you're playing a game, and I'm sure you are. I mean, you're not thinking about work or whatever else bothers you, but you're actually thinking very intensely. And by looking at the different kinds of games that are out there, you see that they actually challenge a very large variety of our cognitive skills. So I would claim that if you have an algorithm or an agent that can play any game you give it to it, or maybe even just any game that's reasonably popular, the top 100 games on Steam or iOS App Store or something, you essentially have general intelligence. In the history of AI, people started out with working on AI for playing chess. And that was an extremely important problem for the first 40 years or so of AI research. And then in 1997, we had IBM's Deep Blue computer beating the best chess player in the world, Garry Kasparov, and attention moved over to Go. And many people thought that, we beat the humans at chess, but we still don't have artificial general intelligence. Because we can only play chess. Maybe Go requires actually more intelligence. And Go is a different challenge. You have a higher branching factor, meaning you have many, many more different moves you can make. So it was definitely a very significant moment when DeepMind's AlphaGo beat Lee Sedol in 2016. And it's a very, very good work, AlphaGo. I mean, when you look back at it, it's a combination of two ideas. It's about convolutional neural networks, which are very sort of powerful and important in their own right. And then Monte Carlo tree search. And the real sort of invention here was the invention of Monte Carlo tree search in 2006. Because you look at the best computer Go players in the world, you see this qualitative leap in 2016 where suddenly they jumped many, many places and became sort of master level pretty quickly because of this pretty simple statistical tree search algorithm. We use it a lot. You can combine it with evolution in many, many different ways. So in my research, we worked on evolving selection functions for Monte Carlo tree search. We worked on evolving evaluation functions, and also like taking it as a pattern, taking Monte Carlo tree search as a very flexible algorithmic patterns and evolving completely new algorithms that play games based on this general template. So AlphaGo is really, really important for what it represents. It was great engineering, great work. But I would say that the underlying idea of MCTS is the more fertile idea. First of all, coming up with AI that can play games and design games and model players and so on is very, very worthwhile in itself. However, the games industry is culturally and commercially more important than ever. So this is definitely enough in itself. And games as a vehicle for moving towards general artificial intelligence is also a very important aspect of this. But I also see in the future that more and more of what we're doing is going to take place inside game engines. So if you look at architecture, you're building a house. You want to test it with artificial humans moving around. Now, that's probably going to happen inside a game engine. You're building a new shopping mall, same thing. If you're sort of simulating the logistics of your global trade network, I see that happening in a game engine as well, because all the technology is there. And this is going to be the game engines and game-like environments are going to be the natural way to test and simulate all things in the future. So this technology, AI for games, is going to be hugely important there. At the same time, this is not going to be used only for testing and simulating, it's also going to be used for training. So we see game-like training happening everywhere. Training is expensive, because if you want to train someone on your actual equipment, on your actual airplane, on your actual ice cream store, on your actual tax system or whatever you have, that's very expensive. So we see more and more of training moving into games. So you're going to see almost everything that's being made in the future is going to have a game-like simulation that's used for testing the system, developing the system, tuning the system, but also for training people in it. And the technology we develop is going to fit straight in there. So one of the great things with evolution is that it teaches you that you don't know what your problem is. It makes you very humble when it comes to sort of problem definitions. So when I was working on racing games, for example, I would tell it that you need to get around the track as fast as possible. And that was your fitness function. Basically, how many laps can you drive in a particular time? And what you see very quickly is that you have you find a car that basically backs over the goal line, drives over the goal line, so it drives another track, and then backs over the goal line and drives over the goal line again. And then suddenly that means that, okay, you haven't actually written your fitness function well enough. You basically, this is just about passing the goal line. Evolutionary computation is great at sort of solving the problem you stated without solving the underlying problem, without solving the problem you thought you had stated, which really makes you understand that you need to be careful about defining your problems. I also had so many examples of like using the physics of the game to bounce off walls in various ways. Driving backwards, which was an entirely viable solution in some cases. You bounce into a wall and you keep driving backwards. There was no rule against it. You can do it. You won't see it in a real car racing simulation or real car racing in the real world, because people don't think that way. And when it comes to sort of using evolution to create game levels and game rules, we've seen a lot of that as well. So for example, we've been trying to create video games that are playable by people. And we use as a fitness function that we want some agents to play it badly and others to play it well. And you usually find very, very strange rule sets evolve with very strange success criteria, which are, on the one hand, deeply creative, because you wouldn't have thought about it, but on the other hand makes for a very strange game, which might be about estimating the time it takes for an item to go from one place to another. And as a human, you look at this and like, this is not a good game. Or is it? You can't tell. Maybe it actually is good, but you're just not used to it. So evolutionary computation has this creativity that just keeps surprising. Oh, obviously evolutionary computation is much more general than deep learning. Deep learning is using gradient-based learning to train these very large neural networks. It's very useful for many things. Evolutionary computation is something more fundamental, because the basic principle of evolution is the most general learning algorithm there is. And it can be used for deep learning in various ways, creating structures and even tuning weights of neural networks. Whether it is more or less efficient than gradient-based learning in specific scenarios is an empirical question that we'll see people, you'll see lots of benchmarks fighting it out over. You'll see people doing theory about this, and that's good and everything. But I think evolutionary computation has this quality which gradient-based search as a backpropagation does not have. You can phrase it, I recently phrased it in terms of a central debate in 20th century epistemology between inductivists, so the logical positivists, and the critical rationalists, like Karl Popper and his successors. Whereas the positivists saw learning as induction. You basically, the impressions in your brain are caused by what you see, and the sort of knowledge is sort of more or less automatically built up what you see. You accumulate knowledge. And then Karl Popper, the great philosopher of science, and his followers would say that, well, that's not how knowledge is created, at least not interesting knowledge. Like, I mean, the theory of, special theory of relativity, E equals mc squared, it won't come out of observations. You can't do that by just looking at lots of things and sort of, generalizing from them. It's about something you invent and then test against experience. So backpropagation and gradient-based search in general is like logical positivist induction. It's not going to come up with great ideas. Evolutionary computation is like critical rationalism. It invents things and tests them against experience. So whether backpropagation will have a place in any future sort of general AI architecture, well, we'll see. It probably will. But evolution will definitely have a central place. Evolutionary computation, I don't know what the problem is. Or I don't know what the problem would be. But it would be something where we are not very clear about what the problem is. Evolutionary computation, sort of next grand challenge, will probably be something where the success criteria they are not very well defined. It's a little bit like this famous American judge who said that I know it when I see it. I can't define it, but I know it when I see it, speaking about something completely different. I think what evolutionary computation will come up with that will wow us all will be something that is ill-defined. I don't know what that is yet, but I keep thinking about it. There are several big problems. One of them relates to deep learning. We need to be able to handle very large parameter spaces, millions of parameters, maybe billions of parameters. And we need to do that in a way which scales seamlessly with fitness, which parallelizes well, and so on. The other is to combine this with multiple objectives and diversity in solutions. So the quality diversity framework, where you're looking for both good solutions and very diverse solutions, is extremely promising. It's a nice conceptual advance of recent years. And I think that combining this with a multi-objective framework, where you have multiple objectives, will give us tools for tackling problems that other AI methods can't tackle at all. I think something that's often overlooked with artificial evolution is how creative it is and how well it works for tasks that are usually deemed creative, that require creativity to solve. I mean, almost anything we do requires creativity to solve, but generative stuff, creating arts, creating structures of different kinds, that's where evolution tends to really shine. And these are things where you basically cannot usually follow a nice gradient from like a bad solution to a good solution, but you try very many different things. So I think when you think about what evolutionary computation is really good for, look at things that require creativity. And don't let yourself be constrained by your notions of what a human does when a human is creative, or what human creativity is.